Hello and welcome. This video is for students of control systems who have not encountered the Laplace transform before. Prior knowledge of algebra, partial fraction expansion, linear factorization, and differential calculus are assumed. After watching this video, you should be able to solve simple first-order circuits using the Laplace method. Consider the simple circuit shown. We are going to establish two conditions in red that are important to the simplicity of the solution. First, we are going to close the switch at t equals 0. And secondly, upon closing the switch, the capacitor has no initial charge. So, we write a Kirchhoff's voltage law equation which, as you can see, sums the voltages around the closed loop. The capacitor equation for the current is then used with the resistor to give a voltage term, which is added to Vc, the voltage across the capacitor, to get V as shown. We then make the derivative the subject of the equation. Now, when we're developing the Laplace transformation, we have to consider the function ut. The function ut is just a simple function that goes from 0 to 1 at exactly when t equals 0. And it successfully models a switch. V multiplied by ut is actually the behavior of the voltage source and the switch in series, as shown in the diagram. We write the Kirchhoff's voltage law equation in green to be used for the Laplace transformation as shown. We can take the Laplace transform of each of the terms in the equation because there is an exact equivalent in the transformation table. You can see the transformation table that converts between the time domain and the S domain on my website or anywhere on the internet. When we look it up in the table, we see the equivalent terms in the table for the S domain as shown. We then proceed to collect up the terms so that we can make VCS the subject of our equation, which is done in the following line, as you can see. But now the brackets contain an expression in S that we cannot find in our table. So what we need to do now is a partial fraction expansion in order to simplify it so that we can look up the terms in our table. We will return to that in a minute. We now proceed to work on our time domain equation on the left. First, we need to separate the variables and integrate. As shown, the variable that we are integrating on the left of the equation is a simple 1 over x. We are integrating essentially 1 over x, which gives us ln. And on the right side, when we integrate the derivative, we end up with the function t. Now we consider what happens at t equals 0. This is why it's so important. At t equals 0, the value of k is going to be minus ln v, because the Vc is actually 0 as well, as per our initial condition. So finally we substitute that, we rearrange it, and we have the expression shown at the bottom on the left. We now return to our time domain equation on the left. We know that ln is the natural logarithm of the exponential function, and we just make VC the subject and gather up terms, and we come to our familiar expression at the bottom, which basically says to us that VC starts from 0 and rises to a maximum voltage of V, the power source, over a period of time determined by the time constant 1 over RC, and the curve is the exponential function. And we now return to the Laplace equation on the right. We have separated it there into partial fractions. We need now to solve for A and B. And when we do that, we end up with A equals V and B equals minus V. We plug that in to our partial fraction expansion. And then finally, we look up these two terms in the Laplace transformation table. The reason why we can look up some terms individually in the Laplace transformation table is because the Laplace transform is a linear transform and behaves according to the law of superposition. So when we do that, we end up with the following expression. This is just by writing down the Laplace transformation terms as shown. And all we need to do now is to realize that we can remove the function ut and collect up terms, and we end up with our identical solution. And isn't it wonderful? And I want you now to go and enjoy trying this method on other simple first-order equations that you might be able to deal with either in physics or electronics. Thank you for watching this video, and we'll see you soon again in the next video.